Hello students, today we are going to learn some basic ideas regarding small oscillations and certain other basic definitions which are quite important to study the further theory of small oscillations. I am sure that you are all familiar with small amplitude oscillations. When you have learned spectroscopy, or when you learn condensed matter physics, talk about the vibrations of atoms in solids, every time you talk about harmonic oscillators, and we talk about harmonic oscillators with amplitude, small amplitude oscillations. And today we are going to discuss a little more about it. As now you are aware that small amplitude oscillations are very important for learning physics because they are quite important in several important areas of physics, whether it is spectroscopy or like as I said, studying the vibration of atoms in solids, in the case of mechanical coupled oscillators, in the case of electrical circuits, everywhere it's quite important. Now you have seen or you have understood about single oscillators, a simple pendulum you can understand. Then you might have also seen the problems of two coupled oscillators where you have two masses connected to springs which are coupled between two, or there can be pendulum, a simple pendulum, and then another pendulum connected to that. They are coupled double pendulums. So when the solution, or when you are going to um, work on the theory of such coupled oscillators, then the things becomes more and more complicated. I think you all have learned to solve simple harmonic oscillators, but it's quite easy. But when we come to the coupled oscillators, the things becomes more complicated. But many interesting facts or very interesting ideas are actually hidden in that coupled oscillators. So, so we are generally speaking, suppose you have two coupled oscillators, then basically you can see that in the case of small amplitude oscillation, the general motion of these two these coupled oscillator can be considered as the superposition of um, two independent simple harmonic oscillations. You know that they are basically two pendulums connected to each other. Then we can say that the total general motion of this coupled pendulum can be considered as the superposition of two independent simple harmonic motions, which is both of them going on simultaneously. And these two simple harmonic motions we normally call as normal modes. Okay, so we call these two. I said that in the case of coupled oscillators, if I have two coupled oscillators, the total general motion of the system can be considered as a superposition of two simple harmonic motions, and each of these motion are termed as normal modes. Each of these motion are normally called as normal modes. Suppose now and you have, so this is the case of, so I can say that if there are two pendulums coupled to each other, or it is a double pendulum, then I can say that there will be two normal modes. But now if we have n independent such n coupled oscillators, say if I have n coupled oscillators, then it is interesting to see that the general motion is actually the superposition of n independent simple harmonic motions, and I can say that n independent normal modes will be there in the case of n coupled oscillators. Okay, and each of this mode will have its own frequency and wavelength. So each mode will have its own wavelength and frequency. Okay, so they are all separate for each nodes. Okay, that you will come to know. So this is all what we are basically going to understand in this chapter. That is how this, what are actually the small oscillations, and and specifically we are talking about the coupled oscillators, and then in the coupled oscillators what are the different normal modes. So it is all of these things, or we are going to derive the theories of the such coupled oscillators and then discuss about the normal modes. Now before going into the main topic, one more thing you have to get familiarized is about the potential energy. Okay, so about the potential energy and the equilibrium points. Potential energy and equilibrium. So now here we are talking about a conservative system. Okay, so you are familiar, I think you are familiar with conservative system. So when you talk about conservative system, they are those systems whose work doesn't depend upon the path taken by the system. So as you know, the simple harmonic oscillator, which you simple pendulum, is a very good example for that. Or a spring connected to a mass is also an example for such a conservative system. So that means the path taken by the, so suppose if I, this is the initial position, and if I take that the object system to another point, say here, it doesn't, in the case of a conservative system, the work done doesn't depend upon the path it takes, only depends upon the position. So you can see here it is here, and here it is still at a further higher position. So gravitational energies or gravitation is a very good example for such a conservative system. A body working under the gravitational force is a very good example for a conservative system. Okay, now you consider such a conservative system, then you can say that the potential energy of such a system depends only on the position but not on the path it takes. Okay, so I can say that the potential energy is a function of position. Now, as in the case when we come to classical mechanics, we are now familiar with generalized coordinates, and using that only you can talk about the Lagrangian, or Lagrangian is written in Lagrangian formulation. We write Lagrangian in terms of this generalized coordinates. And now let the system, conservative system we are talking about, has n number of generalized coordinates. So there are n number of generalized coordinates. That means they can be q1, q2, etc. Say they are qn coordinates. So now for such a system having n number of generalized coordinates, then the potential energy can be written as, you know that potential energy is a function of position, so I can write it as q1, q2, etc. up to qn. Okay, now what is the force acting on such a conservative system? Force. So we call in the Lagrangian formulation this force as the generalized force. Okay, so it is generalized. Okay, so generalized force acting on the system can be written as gk, and this is equal to negative of this negative potential gradient of the negative gradient of this potential. So I can write it as minus, you have it, that is minus del v, negative of the gradient of the potential. So I can write it as minus dou v divided by dou qk. Okay, so where you know that k varies from 1, 2, 3, etc. up to n. So consider system, conservative system, whose potential energy is given in terms of its position coordinates like this. Okay, and then the generalized force for such a system can be written as, for the conservative system, this generalized force can be written as negative gradient of the potential, so minus dou v divided by dou qk. Now suppose the system is in equilibrium. So what happens if the system is in equilibrium? For a system in equilibrium, that means the system is stationary, right? So no net force is acting on the system. So then I can say that in equilibrium, the net force is equal to 0. So that means I can say that Gk, which is equal to minus dou V by dou Qk, at equilibria it is equal to 0. So I can say that the potential energy has an extremum, and that means that since the force is becoming 0, what I can say that variation of V with respect to Q is equal to 0. That means that the potential energy has the extremum. Whenever you have studied in mathematics that if you draw a curve and with respect to a coordinate, so here there is a potential energy drawn with respect to the coordinate, so that Q. So I can say that when should this differential become 0? If this differential becomes 0 only when at the positions where the potential energy V is maxima or minima. So that means if the equilibria or the net force has to become 0, that means at equilibrium the net force becomes 0. So I can say that at equilibrium then the potential energy has an extremum. Potential energy has an extremum value, So it can be it can be a maxima or a minima. So now if the system is in equilibrium with 0 initial velocities, with a system is in equilibrium and there is no initial velocity, then the system will remain as such indefinitely, right? That is, the potential energy will be maximum. It can be, if I draw this potential energy with respect to the, this is potential energy, and with respect to the coordinate Q, if I draw, it can be either at this point, and this is the equilibria point, which means the potential energy can be maximum, okay, at the equilibria, or you can say I can draw this in this way also, that is, in this way, this is also an equilibrium point because potential energy is at the minimum value at this point. So if a particle or if a system is at this state with the initial velocity 0, it will remain as such indefinitely. And here also, if the system is in this position at the minimum of the potential energy curve, or it is possessing the minimum potential energy, and if no initial velocity is 0, the system will remain in this position alone. It will indefinitely. Okay. So now on the basis of this equilibria, there are different types of equilibria where the system is in the highest of the potential energy, where the system is at the lowest point of the potential energy. So based on that, you can divide. There are different types of equilibria, and that is what we learn as stable, unstable, and then there is one more, and that is neutral equilibrium. So these many equilibrium conditions are there. Okay. Now I have shown here 3 kinds of equilibria. Okay. A system is said to be in stable equilibria when the system is at the bottom of a potential energy curve. So you see that this is the potential energy curve. As I said, as you climb here, the potential energy will be higher, and it is the position where the potential energy is low. So now the system is lying in the lowest point of the potential energy. Now what happens if I move the system, or if I give a small displacement to the system? You know that what happens, right? The ball may, suppose if I move it, displace it to this position, it will move. It may come here. That depends upon the force I give. But then if I simply make it displaced, it will go till here and again it will come back, right? Then it will make an oscillation like this about this equilibrium point. So that means a system is said to be in such kind of equilibria, that is, if a small displacement of the system from the rest position, if I make, it will result in a small bounded motion about the equilibrium position. Okay, anyway, it will have the tendency to come back to its equilibria, but it may again have a bounded motion, but still finally it will come and fall into the equilibrium point. Then such kind of equilibria are called as the stable equilibria. Now you consider the second case, unstable equilibria. Now you see the system is here and the potential energy is the maximum for the system. Now what happens if I simply displace it? It will finally, if it is in this way, it will come and finally fall here, right? Or if I make the displacement this way, it will come and finally fall here. It will never make an bounded motion. It will never come back to its equilibria point. So a small displacement made to the system from the equilibrium position results in an unbounded motion. Okay, results in an unbounded motion. Here it was bounded motion. It is unbounded motion, and then and system will never have a tendency to come back to its equilibria, and such kind of equilibria is called as unstable equilibria. Now there is another one more, that is, it is a simple case which we normally see, right? So if I put a coin on the table and you just simply displace it, the coin, what happens? It will go and come here, lay here. It will never come back, or nor it will never go back away to the equilibrium position. Like it will never have a tendency to come back, or it will never have a tendency to go in this way. So based on my displacement, it will simply based on my force, applied force, it will simply make a displacement and it will lie there as such. Okay, and such kind of equilibria are called neutral equilibria. So the best example is a coin placed at the flat on a table and it is in equilibria, I can say. And this is like example normally very always talked example for here is egg standing on one end. Egg, when you make it stand on one end, and if you simply actually displace it, it will never come back to its original standing position. But now this is simply a bowl you consider, and then you put a, or a simple example is simple pendulum is also a very good example. Or you get a bowl and then you place a small ball or a something, a bob, then you start actually displacing, it will make a bounded motion. So these are the different kinds of equilibria which we may have to study, or we may come across in many discussions. So that is so these are the fundamental concepts when we go studying the small amplitude oscillations. Okay, so now you might have been familiar with the different kinds of equilibria, then different kinds of potential energy curve, and all these things. So if you have any clarifications, you may please comment. So for the time being, we can stop and we can see in the next session. Thank you very much.